Today we want to introduce the gradient and talk about directional derivatives. At this point, we're familiar with dc dx, which is going to be the rate of change of z in the x direction. And we'll talk about dz dy, which is the rate of change of z in the y direction. But that's only two directions on a plane, horizontal or forward and back, and then left and right. That's only two directions, and we have an infinite number of directions. We got 360 degrees going around on that plane. We can't just concern ourselves with the x direction and the y direction. So really, the problem that we're facing right now is that there are more than just these two directions. We got x direction and the y direction, but there are more than these two directions. There's more to R2 than these two directions. And we might want to know how z is changing in some other direction. We might want to know the derivative in some other direction, something other than the x direction, something other than the y direction. What we're going to have to do is combine the x derivative and the y derivative in some fashion, and then combine that with some other direction to find out how much z is changing in that other direction. So we got to think about what we use to make directions, and we use vectors to make directions. So I'm going to have to somehow make a vector out of these derivatives. Then I'm going to have to figure out the direction that I want to calculate the derivative, and then how to combine those to find out how much z is changing. So I'm going to make a vector out of my derivatives. I'm going to make a vector to be the direction that we want, expand on this just x direction and just y direction. And I'm going to take those two vectors and combine them in some way that tells us how z is changing in a particular direction. I'm going to be combining two vectors to make a scalar. And already the rest of this discussion is done. I'm going to take two vectors and combine them to make a scalar. What operation am I going to have to use to make that happen? How am I going to make a vector out of these derivatives? So let's talk about the gradient. Let's suppose that z is some function of x and y. As usual, we're going to start by looking at functions. We're going to make a relationship between x, y, and z, and it's going to be a function relationship because functions are the easiest place to start. We can write one variable as a function of the other variables, then our work is a lot easier. Think about describing functions, y is a function of x, versus equations in x and y, like x squared plus y squared equals r squared. So an important thing to note, the gradient is going to be a vector. And it's going to be a vector in which we combine the two derivatives of the function. We're going to use as notation grad f for gradient of f. The gradient of a function at a particular point x, y is going to be the x derivative at xy in the I direction plus the y derivative xy in the j direction. If I asked you to combine the two derivatives into a vector, this is probably what we would have come up with. That's why the gradient is so awesome. This is just what we would have guessed anyway. We would have maybe tried to do some weird stuff. What if we put the x with the j and the y with the I? But that would be weird. The first thing that would have occurred to us is the thing that we want. That's amazing. It's like when you get into linear algebra, I say, how are you going to add these matrices? The first thing that you would guess is what you would do. Now, when it comes to multiplying matrices, not the first thing you would guess. Because the first thing you would guess in multiplying matrices doesn't actually tell you anything useful. And when we actually multiply matrices, which is really weird, that does tell us useful information. But this is the first thing that we would have guessed anyway. Here's some interesting things to know about the gradient of f. The gradient points in the direction of maximum increase. The gradient points in the direction of maximum increase. So the gradient will point in the direction of the maximum increase of f. We can think of it as the steepest route up the hill. So think of it as the steepest route up the hill. Think of the gradient, the direction of the gradient, as pointing in the steepest route up the hill. On a contour map, we're going to see that the gradient is perpendicular to the contour line. So the gradient is going to be perpendicular to the contour line. Pause for copying. Oh, I don't need to read that part. The gradient will be perpendicular to the contour line. So if we have some function out there with a bunch of contour lines, the gradient is a vector. So let's suppose we got a bunch of contour lines. Let's show that they're increasing. So this one is at 30. Here's where z is 40, and here's where z is 50. At a particular point, x, y, the steepest way to get from 40 to 50 is going to be perpendicular to the contour line at 40. Let's talk about why this makes sense. The contour line is telling us where the function isn't changing at all. So if we travel tangent to the contour line, no change in the function. perpendicular to the contour line, maximum change in the function. This is so organized, it makes me barf. This is perpendicular to the contour line. This makes perfect sense. The contour line is showing us where the function isn't changing. The contour line is where the function is constant. Every value of the function along this contour line of 40, the value of the function is equal to 40. So if we travel tangent to the contour line, the derivative will be 0. The derivative tangent to the contour line is 0. The derivative perpendicular to the contour line is maximum increase. If we point the gradient in the other directions, and so instead of going from 40 up to 50, if we take minus gradient, that'll be the direction of maximum decrease. And that'll just be the perpendicular, going perpendicular to the contour line in the other direction. Tangent, the rate of change is 0. Perpendicular to the tangent to the contour, the rate of change is 0. Perpendicular to the contour, the rate of change is maximum. Is everybody okay? So let's talk about calculating the derivative of a function in some other direction, not just in the x direction, not just in the y direction. It's going to use this gradient, which tells us how things are changing in the I and j direction. It's a way to take our derivatives and make them into a vector. And let's talk about the directional derivative . So we would want to calculate, say, the derivative of a function f in the direction of a unit vector. We're going to want to specify the direction with a unit vector because all we need from this vector is the direction. So the derivative of f I believe that this book uses u for the unit vector. Makes sense, u for unit vector. It also uses v for unit vector. I respect them for using u for unit vector because of the notation that we use for this. Now we use f subscript x for the derivative of f in the x direction. We use f subscript y for the derivative of f in the y direction. So if I want to indicate the derivative of f in the u direction, where u is a unit vector, that means u has a length of 1. I just use f subscript u. So the derivative of f in the direction of unit vector u is denoted fu. Especially because we don't say sub in front of things a lot of times, we just say fu. So fu is, I'm going to have to somehow combine my gradient vector and my unit vector to come up with a scalar that describes how much the function is changing in the direction of the unit vector u. How do we combine two vectors to come up with a scalar? You were thinking dot product. I told you at the beginning that this lecture writes itself. It's exactly what we would guess. We just take the gradient of f and find the dot product of the unit vector u. This also tells us why we need to use a unit vector, because we're throwing the unit vector into the dot product. And all I want, the only information I want out of the unit vector is the direction. I don't want to have any length changing what's my my instantaneous rate of change. If the unit vector is not a unit vector, but has a length of 2, then I've just taken my derivative and multiplied it by 2. It's twice as big as it needs to be. Because the dot product of the gradient and the unit vector is going to be the magnitude of the gradient of the unit vector. Sorry, the magnitude of the gradient times the magnitude of the unit vector, which is 1, times the cosine of the angle between those two vectors. And I want to get all my magnitude information out of the gradient. So if we think about what the dot product represents, I'm going to take, nope. I'm going to take the magnitude of the gradient times the magnitude of u. Since u is a unit vector, that's going to be 1 times the cosine of theta. So the derivative of f in the direction of unit vector u is the gradient dot the unit vector, which is also calculated the magnitude of the gradient multiplied by the magnitude of the unit vector multiplied by the cosine of the angle in between those two vectors. And now it makes even more sense, the stuff that we were talking about with regards to the gradient. If we set the unit vector up to be tangent to the contour, then the angle between the gradient and the contour is 90 degrees, and the cosine of 90 degrees is 0. If I set up the unit vector to be perpendicular to the contour, then the angle between the gradient and the unit vector is 0 degrees, and the cosine of 0 is 1. And that's the maximum value of the cosine of theta. Cosine of theta is at maximum when theta is 0, and 0 when theta is equal to 90 degrees. I suppose I should be using pi over 2 radian. I have a trig class, so I'm probably going to be describing things in degrees a lot. Any questions? Yesterday we calculated some derivatives. The derivative in the x direction was 4. So when x increases by 1, we expect z to increase by approximately 4. And the derivative in the y direction was -2. When y increases by 1, we expect z to decrease by 2, approximately. Now we're just taking that 4 and 2 and making them into a vector. That vector will be 4i minus 2j at that point. And that will show us the direction that is perpendicular to the contour. Any questions? How's everybody okay? We like examples. Let's do an example. So here's the kind of question that we might ask. Here's a function, might look familiar. F of xy is 9 minus x squared minus y squared, and I want to find the derivative of f at a particular point. Remember, derivatives is a local thing. They happen at a point. The derivative of f at the point 2, -1 in the direction of this vector v, which is 3i plus 4j. We're calculating a directional derivative, which means I need the gradient. So fx at xy is going to be minus 2x. And so fx at the point 2, -1 is -2 times 2 or -4. Fy at xy is -2y. So Fy at 2, -1 is -2 times -1 or +2. This just represents how f is changing in the x and y direction. I can combine them into the gradient and say that the gradient of f at the point 2, -1 is going to be the vector -4i plus 2j. The other thing that we need is a direction to calculate the derivative in. A direction in which to calculate the derivative. And the direction that we're given is 3i plus 4j. I can't use 3i plus 4j. That's not a unit vector. So we'll make that a unit vector. So the magnitude of v is going to be the square root of 3 squared plus 4 squared, which is the square root of 25, which is 5. That's why I picked 3 and 4. So a unit vector in the direction of v just take the vector v and divide by its length. Scale it down to a length of 1. So if I want the derivative of f at the point 2, 1 in the direction of 3i plus 4j, denoted fv at 2, -1, I'll take the gradient of f, -4i, plus 2j dot the direction vector, direction unit vector, 3/5 I plus 4/5 j. We're going to be combining these two vectors with a dot product. So we're going to come up with a scalar. So I'll have negative 12/5 I, or sorry, negative 12/5 plus 8/5. And that's going to be negative 4/5. Question? Everybody agree? Now we should be looking at this and saying, heck, this homework is going to be pretty easy. Find gradient, that just means finding some partial derivatives, put them together in a vector. Make sure the vector is a unit vector, and then calculate a dot product. This is just section 14.2 combined with section 13.3. So apparently 14.2 plus 13.3 equals 14.5 or 14.4. Weird math on that. When I was in school, I remember all the books when they wanted to break a chapter down into sections. They were always using dash. It was like 14-1, 14-2. But then at some point, they started switching to the decimal point, 14.1 and 14.2. And everything, I guess everybody thought it looked cooler because it looked like a number. Then someone wrote a book with more than 10 sections in it. They'll, well, we'll just call it 14.10. So it'll be like, well, wouldn't that be the same as 14.1? I said, well, not if we do it after we've had a significant figures discussion. Then we'll be okay. But it does make them come out in a weird order if you don't call your sections in your file names 14.01 and so on. All my file names have to be like 14.01, all because there's like one chapter in this 21 chapter book that has more than 10 sections. So my fault. Chapter 11, why did you have to have 11 sections? And chapter 11 is like, oh, because I'm the chapter 11. I'm all 11. Because if we cut two sections out of chapter 11, I can go back to a smaller naming scheme for all my sections. This is like all 14.2. Because chapter 11, 14.02. At least there aren't any chapters with 100 sections in it. At that point, I'll just write the publisher and say, listen, you need more chapters. Questions? Comments? Lines of mark? So, gradient and directional derivative. It's kind of a combination of a bunch of things that we discussed before. And we're putting together these ideas in kind of the obvious ways that we would put together these ideas. It's just more efficient if I say, instead of making you guess, just tell you what the thing is. You know what I mean? Because there's a style of teaching that's like that. Where I walk up here and say, I want to know a piece of information. And I secretly know the answer, but I make you all discover it. And for certain things, this is a great idea. And for other things, It's not such a great idea. Because like the point of school, the point of hiring one person that has been through all the math is so that that person can like answer the questions and tell you the stuff. You know what I mean? Anyway. All right. I know it's really weird to have two short discussions in a row. But that's going to do it for today. I will see you all on tomorrow. Finish up the first half of chapter 14. Everybody have a good day, and thanks for playing.